In this video, I'm going to talk through the AQA Physics GCSE Unit 2B pre-exam PowerPoint that I'm going to use with my classes. I hope you enjoy. The first thing we're going to look at is the difference between alternating current and direct current. We're going to look at direct current first. Direct current is produced by cells and batteries, and direct current flows in one direction only. So you can see over on this side we've got a graph, and you can see that direct current goes in one direction only, and it doesn't oscillate, so it doesn't change at all. If you obviously left the device on for a long period of time, what you would see is that current would slowly decrease with time. So now we'll look at alternating current. Alternating current is produced by the mains electricity. It changes direction many times each second. When you look at the graph, you can see the idea that the alternating current is oscillating. Okay, so it changes directions many times each second. And you can see here that it goes through one complete cycle in about 0.02 seconds. That's equivalent to the main supply of the UK, which produces a frequency of 50 Hz. Okay, which means it cycles 50 times every second. It also has a potential difference of 230 volts. You can see a maximum 230 volts there, and obviously when it's oscillating in the opposite direction, it'll go down to minus 230 on this axis. The other thing you need to be aware of is how you would work out the frequency from a graph display such as this one in the alternating current. So how you go about doing that is, first of all, you work out a time period from your graph. Now a time period is the time taken for one complete oscillation. You can see that one complete oscillation starts here and finishes at this point here. So the time period is equal to 0.02 seconds. You also need to know the equation that frequency is equal to 1 over the time period. So that will equal 1 over 0.02. And you will work that out. If you put that into your calculator, you'll find that therefore the frequency will equal 50 Hz, which is equivalent to the main supply. The next part we're going to look at is the safety feature of the 3-pin plug. In the UK we use a 3-pin plug which contains 3 different wires inside. Those 3 wires are coated with an insulating material that has different colours on. The earth wire is yellow and green stripes, the neutral wire is blue, and the live wire is brown. The 3-pin plug also contains a fuse, a cable grip, and an insulation that goes around all 3 wires when it leads to a cable. The cable grip function is to hold the cable in place so you don't get the cable sliding down and exposing the 3 smaller wires. The live wire of a plug alternates between positive and negative relative to the earth, and that's the direction that the electrical current will flow into. The live wire is connected to a fuse, and the fuse will melt if there's a surge in electrical current. So if the electrical current goes above the fuse value, the thin wire inside the fuse will melt, and that will break the circuit. The neutral wire of a plug stays at a potential close to 0 relative to the earth wire, and that is the direction in which the electrical current usually leaves the plug. The earth wire is an extra safety feature, and it has a very low resistance, and it's there in case there's a fault inside the plug in which electrical current is not flowing where it's supposed to be. In that case, the excess electrical current will go through the earth wire because it has such a low resistance. The low resistance of the earth wire then causes a higher current to be drawn from the supply. The higher current then will exceed the fuse value, and that will cause the fuse to blow, and that will disconnect the circuit. We are now going to look at power and fuse values. Power is the rate of doing work, and the amount of power being used by an electrical circuit is given by the equation power is equal to voltage times current. Power is measured in watts, voltage is measured in volts, and current is measured in amps. Power can also be related to energy, and the power rating of an appliance is simply how much energy that appliance is using every second. So power can be calculated as well using the equation power equals energy over time, where energy is measured in joules, power is measured in watts, and time is measured in seconds. Once you've worked out the power rating of your appliance, you'll be able to calculate the current flowing through it using the equation that we've already talked about, which is the idea that power is equal to voltage times current. Remember that a fuse has that symbol, that's the circuit symbol for a fuse, and when you choose a fuse, you should always select a fuse with a slightly higher rating than the current that flows through the appliance. So if you were to have a bulb which has a current of 10 amps flowing through it, the fuse that you'd want to choose would be slightly higher than 10 amps. So of these 3 fuses to choose from, you would choose a 13 amp fuse. That means that the current of 10 amps can flow through the circuit without melting the fuse. Next, let's look at background radiation. Background radiation is around us all the time. We can do little to avoid it. Most background radiation comes from natural sources, while most artificial radiation comes from medical examinations such as X-rays and photographs. Here we have a pie chart showing the different types of background radiation. You can see that the majority of background radiation comes from radon gas that's emitted from the ground. You get 11.5% from food and drink. Cosmic rays, which is another natural source, that's rays coming from the sun, count 10%. And gamma rays from the ground and buildings count 14%. That means that we only get 15% of our radiation from artificial sources, and the artificial sources where we get radiation from are medical examinations or x-rays, and then we can see some from sort of occupational roles and jobs, nuclear discharge, and nuclear fallout. The thing to remember about background radiation is that we must always remove it from our measurements when we take sort of count rates. So if we were trying to work out the activity of a radioactive source, we would first measure the background radiation using Geiger counts like the one shown here, and then we'd have to subtract the background count away from our counts that we get when we're using radioactive sources. We are now going to have a look at the atom. The atom is made of three particles. They're called the protons, neutrons and electrons. Protons and neutrons are usually found in the centre of the atom in a place known as the nucleus, and you can see that protons and neutrons are found in the centre there. The electrons, however, they orbit outside the nucleus in things called electron shells, and you can see them orbiting around the nucleus on these pathways here. So the electrons are the particles in black, the protons are the particles in blue, and the neutrons are the particles in red for this diagram. You also need to be aware of the different relative masses and relative charges of each of the particles. And when we talk about relative mass and relative charge, we're talking about those relative to the proton. So the proton has a relative mass of 1, and its charge has a relative charge of 1 as well. When we compare the neutron to the proton, they have about the same mass. So the neutron has a relative mass of 1. However, the neutron is not charged, so it has a charge of 0. The electron has a relative mass compared to the proton of 1 over 2000. And its relative charge compared to the proton, well, it has the opposite charge, so we indicate that by saying it's a negative 1. The great thing about the atom is if you truly understand it, you can apply that information that we've got here from the atom to talk about things such as electricity, nuclear physics, atomic physics, and it really helps your understanding in those areas. When we look at the periodic table, we can get lots of information from the periodic table. The first thing to understand is the atomic mass number, or nucleon number as we like to call it in physics. And you can see that we find this at the top here. And the nucleon number is the number of protons plus the number of neutrons. We've then got the atomic number or the proton number, and that is the number of protons. Now for an atom, that's usually the same as the number of electrons. The only cases where you'd have a different number of electrons to the number of protons would be if you had an ion. And just a reminder that an ion is an atom that has gained or lost electrons. The elemental symbol can be shown here. So for this example, we've got helium, and that just tells you which element you're looking at. So remember that this is the number of protons, the atomic number or proton number. The atomic mass number is the number of protons and neutrons. So therefore we can work out the number of neutrons in this example for helium will be 2. And the way I've worked that out is I've done 4 minus 2, which equals 2. We're now going to have a quick look at isotopes. So isotopes are the same number of protons but a different number of neutrons. So usually we have carbon-12, but you can see that carbon-14 has got 2 extra neutrons, but he's got the same number of protons. So carbon-14 is an isotope of carbon-12. We're now going to look at nuclear radiation. Nuclear radiation is emitted from the nucleus of an atom. There are 3 types of nuclear radiation, and those are alpha, beta and gamma. Alpha radiation is a helium nucleus which contains 2 protons and 2 neutrons. Beta radiation is an electron and is emitted when a neutron turns into a proton. Gamma radiation is a high-energy electromagnetic wave, usually given out after one of the other forms of nuclear radiation is emitted. We are now going to look at the different properties of alpha, beta and gamma. Alpha radiation is a helium nucleus I've already mentioned. It's got a relative mass of 4 because it contains 2 protons and 2 neutrons, and therefore 4 nucleons. Its relative charge is plus 2 because it's 2 protons give it a plus 2 charge. Bear in mind it's a helium nucleus, so it contains no electrons, so you've just got the positive protons there to give it a plus 2. It's the most ionizing. Remember that ionization or ionizing means that an atom is turned into an ion. Alpha is the most able to ionize things, which is the heaviest and the largest of the nuclear radiations, so is more likely to strike atoms and cause them to become ionized. The fact that it's the largest also means that it's got the least amount of penetration, so it'll actually travel the shortest distance in air. In terms of the material required to stop alpha, that material is paper. Having a look at beta now, so beta emitted a high energy electron. Beta is emitted usually when a neutron turns into a proton in the centre of the nucleus. So a neutron will turn into a proton, that will release a high energy electron to balance out the charge. The relative mass of a beta particle is the same as the electron, which is 1 over 2000. The relative charge of a beta particle is the same as the electron, which is -1. It's got a medium amount of ionization, so it's more ionizing than gamma, but less ionizing than alpha. It's got the medium amount of penetration, so that means it's more penetrating than alpha, which will travel further in air than alpha, but it will travel a lot less far as gamma, so gamma travels the furthest of them all. In terms of things required to stop beta, that's just a thin sheet of aluminium. So we'll now look at gamma. So gamma is an electromagnetic wave. Okay, it's got a relative mass of 0 because it's a wave, it's got no mass, and it's got a relative charge of 0 as well because electromagnetic waves are not charged. It's the least ionizing, so it causes the least amount of ionization, so it causes fewer atoms to be turned into ions, but it's got the most penetration, so it can travel the furthest through air. The materials that you need to stop gamma is lead or concrete, and you tend to need quite a lot of it as well. We're now going to look at radioactive decay equations, and the first ones we're going to look at are the ones for alpha radiation. So remember that alpha radiations are made up of 2 protons and 2 neutrons. In alpha decay, the nucleus that you start with will emit an alpha particle from the centre of the nucleus. That means that the nucleus will decrease in size by 4 nucleons. 2 of those nucleons are protons and 2 of them are neutrons. So when we look at our decay equation, we can see that our proton number decreases by 2 because we've lost 2 protons with the helium nucleus, which is the alpha particle. And our nucleon number decreases by 4. That's because we've lost 4 nucleons, remember 2 protons and 2 neutrons, when we emit our alpha particle. So we can apply that convention now to the questions below. So you can see that for question 1, we have x is 181 and 72 to begin with. So what will our particle y have in terms of its atomic number and its atomic mass number? To look at atomic number first, we're going to see that we've lost 2, so we do 72 minus 2 to give us our atomic number as 70. In terms of the atomic mass number, we've lost 4 nucleons, so 181 minus 4 will give us 177. So we have 177 as our nucleon number or our atomic mass number. In example 2, our atom that began with as X4193, we can see again we do the same thing, so our 41 is going to decrease by 2, so 41 minus 2, which will give us 39, and our 93 will decrease by 4, which will give us 89. That's our correct answer there. After you've finished a radioactive decay like this, you should always try and add them back together. So 89 add 4 you can see gives me 93, so that will be correct. And 39 add 2 will give me 41, so that one will be correct. If it goes to one above, 177 add 4 gives me 181, which is correct. And 70 add 2 gives me 72. This is based on the fact that mass must be conserved and you're not losing mass between each interaction, nor are you losing charge between each interaction. We'll look at beta radiation radioactive decay equations now. So remember that beta particles are electrons, and beta decay occurs when a neutron inside the atom turns into a proton. Now in that process we've got a neutron turn into a proton. So our number of nucleons stays the same. So our atomic mass number or our nucleon number, which is A, stays the same because we've not lost or gained any nucleons, we've just had one neutron turn into a proton. So if one of our neutrons has now turned into a proton, then we've gained 1 in terms of our proton number or our atomic number. And remember that the beta particle is given out is an electron, so it's got a -1. And you can see again, to balance this out, we've got Z goes to Z plus 1 minus 1, we just go Z to go into Z, which means that the mass and charge is conserved. So we're going to apply that to some equations now. So in the first example, remember that our nucleon number stays the same. So we're just going to have 14 here, because it's just the same. Whereas our proton number, we have to add 1 to. So 6 plus 1 gives us 7. Let's just check that. So 7 minus 1 will give us 6. So that is conserved, which is good. We move on to example 2. So remember our nucleon number, 119 nucleons. Well, that's not changed, so we have 119 there. I remember again we do 94 plus 1 this time to get 95. I can do our double check. 95 minus 1 is 94, so again it's conserved. And that is how we do radioactive decay equations for beta. We're not going to look at the radioactive decay equations for gamma rays. The reason we're not going to look at gamma ray radiation is that gamma rays have no relative mass or relative charge. Because they're electromagnetic waves, they have no charge and no mass. And therefore when a radioactive particle emits a gamma ray radiation, all that's happening is that it's emitting excess energy. So usually what happens is that when a particle decays through alpha or beta, it's left in an excited state, which means it's got excess energy, and it will emit that excess energy as a gamma ray. We're now going to look at the nuclear fission. So nuclear fission is started when a neutron strikes a large nucleus. The neutron causes a large nucleus to become unstable. The large nucleus will then split into two smaller nuclei, releasing 2 to 3 neutrons and energy. So as I've said already, to start the process you fire a neutron into a large nucleus. Nuclear reactors use uranium-235 most commonly, and sometimes plutonium-239 as their fuel sources. So in a nuclear reactor we're usually firing a neutron into either uranium-235 or plutonium-239. The neutron causes a large nucleus to become unstable, and that large nucleus will split into two roughly the same size nuclei. That process releases energy, but it also releases 2, or in this case 3 more neutrons. Those 3 neutrons will then go on to form reactions of their own, which will release even more neutrons, and that is the process by which they're called a chain reaction. So each neutron will go and collide with an extra nuclei, or nucleus of uranium or plutonium. That plutonium will then break down in the same way that we've seen here and release 3 further nuclei. So you can see after the first set of reaction we've got 3 neutrons being released. After the second, those 3 will go on to create 3 more reactions that will each release 3. So we'll end up with 9 neutrons being released after the second round. Those 9 will then go on to create 9 reactions that will each release 3. So we'd end up with 27 neutrons after the third round, and that keeps going on and building and building. Now if that was a nuclear weapon, you would just let it run its course and eventually it would all go up in a massive explosion. Whereas in a nuclear power station you need to control that nuclear reaction, and how you do that is by absorbing some of those neutrons using control rods. Let's look at nuclear fusion. Nuclear fusion is the process by which stars produce energy. In nuclear fusion, 2 light nuclei combine together to form a heavy nucleus. This process releases energy. The example below is taken from a star. So in stars we use tritium, that reacts together with deuterium. They undergo nuclear fusion and join together to form helium, and they also release energy and an extra neutron. That brings us to the end of this video. Please watch the other video about stars to get the final part of 2B, and I wish you every luck in the exam. Thank you for watching.